So what we're going to talk about today is digestion, and right now we're going to focus primarily on anaerobic digestion. And I don't know if it's happened to any of you. It's one of those situations where you're on an airplane and the person next to you asks, "What do you do for a living?" And I say, "Well, I work with anaerobic digestion at wastewater plants." They usually pick up their book and then don't say anything else to me. That's why it's nice presenting to industry professionals here. You all kind of know what I'm talking about, and it's not such a foreign and maybe not so pleasant topic that the average citizen is maybe not as interested in. All right, with anaerobic digestion, the key factor is that we don't have oxygen involved, hence anaerobic. It's basically a series of biological reactions that are going to break down the organic matter. And if you wanted to really look at it from kind of a simplistic approach, you have acid-forming bacteria that are breaking down some of these organic materials into acids, and then those acids get further broken down by these methane-producing bacteria, and then they give off the methane, and you also get carbon dioxide. So biogas, or methane, is really everywhere, and these methane-producing bacteria, they've been around on this planet for a long, long time. You know, before the Earth's atmosphere had a lot of oxygen in it, these methane-producing bacteria were active, decaying organic matter, breaking it down, producing biogas. So it's been around forever, and it's only really in the recent years that humans have kind of started to really capture it and use it for productive purposes. Now, as long as humans have been living together in tight spaces, what do we do with the waste has always been a problem. Well, you know, here's a picture of an old Roman bath where they had waste carried off by used bath water. Well, it turns out they were actually pretty bright because they realized that they could take some of the gas that was given off from this waste matter and use it to heat the bath water. That was around the 10th century. And then really not much happened in the area of anaerobic digestion until around the 17th century, when Van Helmont discovered that flammable gases could be obtained from decaying organic matter. And then later on, Volta discovered that the amount of gas you get from this organic matter is dependent on the quantity of this organic matter. That's kind of a simple one. I think I could have come up with that back then, that if you have a lot of this stuff, you're going to get more gas from it. Then later on, really, no one knew what this gas was. It was kind of unidentified. And then Dalton identified the chemical formula for methane. It's carbon with 4 hydrogens. And then it wasn't until the 1800s, or late in the 1800s, that wastewater treatment started to kind of become a little more civilized or seen as a greater need in industrialized cities. And so around 1881, a guy named Morris developed what he called the automatic scavenger. It was basically a crude septic tank. And then a few years later, another guy named Cameron developed what he called the septic tank, and he had it patented. And the city of Exeter decided this is such a great idea, we'll put these things in. And they captured the biogas given off from these little septic tank units and used it to fire their street lamps, which is really kind of a brilliant idea given that year and what they were doing. Around 1906, Imhoff patented his famous Imhoff tank. It's kind of famous in the wastewater industry. Most people have heard of it before. It was kind of an early system for treating wastewater. And then Buswell and Imhoff and others worked throughout the years kind of improving the digestion process, looking at ways that you can optimize it, how temperature affects it, how much time it takes for this material to degrade. And then around the 1950s and 1960s, they really started to understand some of the chemistry that was going on, and Speece and McCarty published kind of a little diagram showing exactly how it works. So it's breaking down that organic matter into organic acids, and one of those primary acids is acetic acid. And then the next step is, of course, those methane bacteria breaking those acids down to create the methane. So anaerobic digestion, it's not just limited to the wastewater industry. There's organic waste in a lot of other industries, farming. One of the more simple examples you see is like a plug flow reactor at a dairy farm, where they'll simply put all the cow manure into a long trough and cover it. That cover's there to capture that methane gas so they can either utilize it. You also see it with a lot of lagoon systems. Very simple process basin, covered it up, some means of capturing that biogas. There's also a number of kind of different anaerobic digestion processes. You may have seen like an upflow anaerobic digester. There's also some high rate ones that use a separator off to the side for liquid solid separation. Most commonly at wastewater plants you'll see kind of a two-stage setup. And then what I love to see is a nice big high rate digestion. This is a classic example of everything that's beautiful about digestion, including the rainbow landing right at the end. It's kind of your pot of gold. So where are we getting our solids to digest? Everybody here is probably very familiar. We've got liquid solid separations in most flow sheets. We're taking solids from your primary clarifiers. These are typically around 3 to 5%. It's a fairly dense sludge and fairly high in volatile matter. We're also going to be seeing solids that are coming off of biological treatment processes. These tend to be lighter in solids content and just a little bit less volatile matter. So that's the food, that's the stuff we're sending into our digester that we're going to feed our bacteria with. And what's the advantage of anaerobic digestion? Well, one of the key advantages is the footprint. You can get a huge tank that doesn't take up a whole lot of space and hold a lot of volume, especially if you're looking at silo or egg-shaped digesters. The footprint is relatively small and you can get an extremely large volume. There's also a lot of toxics that will only be degraded in the anaerobic process. That absence of oxygen helps to break down some of those components. There's less energy required typically with anaerobic digestion. Now, that can be somewhat misleading. You don't have aeration with anaerobic, but you do have energy needs for heating the digester and for mixing the digester. But the advantage of the anaerobic system is that you're creating biogas, and most places will use that biogas to actually heat their digester, so they're offsetting your energy costs. One last advantage is that you generally have kind of less biomass. Now, if you look at the organic components in your wastewater and looked at aerobic versus anaerobic, the big difference is that methane production. That biogas is a huge chunk of what those organics get converted to. And so comparing the two, if methane is something that you think you could utilize, that would kind of lend you more towards the anaerobic digestion. There are a few disadvantages though. It can be very expensive in construction costs and your initial capital costs. You have to make large tanks, generally concrete, and because you're producing this gas that can be hazardous, you have to trap it somehow. So that's either done with like a steel digester cover over the tanks, or maybe some type of a membrane system to cover the tanks or provide for your gas storage. You generally have fairly low effluent quality of your liquids that are coming off your digester, and you don't have the ability for any nitrification. Now, there also can be some process issues with running your digester. They can be kind of sensitive. They're like us. They don't like to eat things that they don't enjoy eating. And so you could have long startup and recovery times. If something goes bad in your digester and you wipe out your population of bacteria, you can have a bit of a headache trying to get it back online. And these bacteria are also more susceptible to environmental changes. They don't like quick changes. Everything has to be kind of slow with them. You don't want to change your temperature really rapidly. They prefer to keep things very constant. So you kind of have to keep a little bit of an eye on your process conditions. All right, if you're going to run a digester, what are kind of the things you want to think of to make sure that your operation is running as good as it could possibly be going? It's kind of a recipe for baking a cake. So the first sign that I can tell when I visit a plant if they are having good digestion is you see some flares that are just blasting away. That means they're making very good methane or high methane production, a lot of volatile solids destruction. It also, though, kind of makes me think, wow, they could be using that gas in a boiler, in a generator or a turbine. So I'm not always a huge fan of seeing the flares, but it does tell me that the process seems to be working well. So there's about 6 items that will help you ensure you have a good anaerobic digestion process. First one, you need a good hydraulic retention time. The longer your food is available to these bugs, it gives them enough time to consume all of that organic matter. If you blast it in and then withdraw it too fast, you didn't get volatile solids destruction, and those bacteria were not able to really do their job. So you need to make sure that your retention time gives those bacteria enough time to do what they're supposed to do. And if you compare anaerobic digestion to other processes for kind of stabilizing biosolids, the retention time is fairly quick, and it can vary depending on the type of digestion that you're doing, but generally, 15 to 20 days if you're running a mesophilic digester at around 95 degrees Fahrenheit. So speaking of temperature, for the most part, there's really two popular temperature ranges to operate, and that just so happens to be the temperature ranges that these bacteria enjoy the most. That first one is mesophilic. Mesophilic is around 85 to 100 degrees Fahrenheit. Almost always you see them run about 95 to 98. Coincidentally, that's kind of the average human body temperature, around 98 or so. It's very common. The bacteria love that temperature, and they're a little more forgiving at that temperature. There are many instances where people are running thermophilic digestion. So thermophilic, you're at higher temperatures, 120 to 135. You can reduce your digestion time, but you pay a little bit of a price. You're going to have more energy costs. You're now heating your digester up to higher temperatures, using more energy, and these bacteria become a little more sensitive at those higher temperatures. So you have to be a little more careful on the operation side. pH in a digester, you're wanting about neutral pH. Again, we're trying to keep all of these bacteria happy. That's where they want to be. But you remember, we're talking about acid-forming bacteria and also methane-producing bacteria. So if we have acid-forming bacteria, they're going to contribute to a lower pH, because as they're creating these acids, your pH can go down. So hopefully, if everything's working in harmony, these two bacteria are working together. As the acids are produced, the methane formers are consuming them and converting it to methane. Loading. Loading for a digester, it's pretty standard practice with a digester. Keep everything in balance. You never want to take out more than you're adding in, especially if you have a fixed cover on top. And you want to make sure that you're adding enough food at a rate that the bacteria can consume it. So one thing to look at is volatile acids over alkalinity. That's a ratio that gives you kind of a good idea of how your process is operating. A lot of guys would say, well, we like to keep track of pH. Well, unfortunately, if you're only looking at pH, something bad can happen, and you're not going to know something bad had happened until you've passed that point of no return. So if you look at that ratio and keep a track of it, your alkalinity is giving you a buffer, and that buffer allows for some variation in pH. So as your acid-forming bacteria are creating more acids, your pH is going to start to go down. That alkalinity gives you some buffer zone to deal with that change in pH before things get too bad. But once your buffer is used up, you'll see the pH drop rapidly. And unfortunately, by the time that happens, it's too late to take action. So if you keep a track of your ratio, you're going to start to notice a change while your pH is still staying constant. And that's that buffer doing its job, keeping the pH where it should be. But if you're monitoring that ratio, you can start to see that change and prevent your digester from going sour. Another thing that's gaining in popularity is some kind of pre-treatment. And pre-treatment can do a number of things. Generally, it's going to help you decrease the amount of biomass you have to deal with and dispose of. Some ways of doing pre-treatment are using some type of algae, maybe a thermal hydrolysis, or also some cell lysis or cell wall destruction with ultrasonic equipment. But my favorite and one of the most important things of a digester is good mixing. Good mixing is paramount to good digester operation, and there's a number of reasons why. You've got sludge coming in, you've got sludge coming out. If it's not getting mixed, your bacteria aren't getting the food they need to do what you want them to do. So mixing that digester, it circulates all of the organic matter, circulates the bacteria, everything's getting spread around, and it's able to do a good job. Temperature, though, comes into play. If you're trying to heat your digester, you have to keep it mixed. That mixing helps homogenize the contents, spread that temperature to be equal around the tank. You don't want hot spots here and there or cold dead zones. And then mixing is also important to minimize foam, scum formation. If you have grit issues at your plant, it's going to help to help grit stay suspended. If anyone here has ever had to clean out a digester that has grit in the bottom, this stuff is like concrete and it's very difficult to remove. And then of course the most important one is to maximize your volatile solids destruction and gas production. Why is that? Well, that's where your money savings is coming in. That methane gas is giving you a resource that you can use to heat your digester, generate power, There's plants that will actually have a methane gas pump on site for all the vehicles on the plant site. So there's a number of uses that you can capture that methane, and it's almost a free resource. Okay, classic problem is poor mixing has led to foaming issues and overflowing of your digester. I think, how many people here have seen something similar to this at a digester with foam coming up over the wall? Well, sadly it happens, right? What can happen with poor mixing, you might get some acid formers that are producing a whole bunch of acid, and the methane bacteria are not getting it spread around enough to catch up. And then they might grab a chunk of it, and so you're getting these gas bubbles building up, and it happens rapidly. It's like open a champagne bottle, and you just get this foam explosion up through the sides of the tank, up onto the surface of the cover, over the wall. It's a huge mess. You don't want to deal with it. And in most cases, and most operators you talk to, if they have good mixing, it really helps to prevent those foaming issues from happening. So this is an example of a good sound of digestion. So as you can hear, bubbling away, all of those gases are being produced and coming up out of the side. That's what you like to hear. That tells you that things are working right and you're getting gas production. So what are the future trends with digestion? Our population keeps growing. We're getting more and more people, which is creating more and more biosolids. So we have to have good ways of disposing of these biosolids and treating them, and minimizing that biosolids production is a huge, huge goal for many utilities. Why is that? Well, land application is becoming more and more difficult. Many areas it's highly restricted and simply not an option. And then landfills are also filling up. That's another consequence of increasing populations, and the disposal fees are going up. So anything that can be done to minimize the amount of biosolids that need to be disposed of is going to greatly help the operations. Another reason anaerobic digestion is gaining popularity in many parts of the country is rising power costs. Particularly in the Northeast, we're seeing a lot of plants that are changing their names from a wastewater facility to a resource recovery facility. And they're having this goal to become a net zero plant where they're utilizing all of their biogas to power as much of their plant as possible. All right, so there's some basics on anaerobic digestion. Right now, we're going to jump in and focus a little bit on some of our newer technologies. The first one being our new linear motion mixer, and then we'll talk a little bit about biogas storage at our membrane covers. If you flip open your old Metcalf and Eddy book, you see a number of different types of digester mixing systems. Most people are familiar with gas mixing systems that either bubble or use diffusers, maybe the lances or bubble guns. There's also big mechanical mixers, like big dough mixers that'll stir the tank. And of course, what was my favorite for many, many years, the draft tube mixers with the mechanical systems and impellers. What we're going to focus on now, though, is a linear motion mixer. There's no rotary motion. It's simply up and down, kind of like a plunger. And I'll admit, when I first saw this thing, my first thought was, there's no way that can work. There's just no way it can work. It's a little plunger. I'll stick with my draft tube mixers. But over time, I've really come to be a huge fan of this mixer and seen numerous places where it has worked fantastic, and the operators seem to love it. The biggest reason they love it, if you look here, all of the maintenance parts are up on top of the tank. The only thing that's down inside of the tank is your hydro disc, which is right here, and there's no real moving parts or bearings or seals or oil lubrication, anything you need to worry about that's down submerged in the digester. That disc sits down in the sludge and moves up and down. You have a gearbox up on top, which is the only area for maintenance. So operators really are huge fans of this.
Anaerobic digestion is an essential step in the water reclamation process. Use of a mixing system, such as the linear motion mixer, helps optimize that process. Ovivo's LM mixer sets the standard for high-volume, reliable mixers. It is the most energy-efficient mixer on the market. The LM mixer uses an up and down motion with a hydro disc to create the desired flow pattern, in addition to impulse waves. There is no rotating motion with the LM mixer. The up and down motion creates an effective mixing pattern by generating a high velocity core, utilizing the pressure waves created by the disc. As shown, two distinct flow patterns are generated from this linear motion. The lower roll pattern that is generated hits the bottom of the tank, where the liquid flows outward towards the walls of the tank. The flow reaches the walls of the tank and moves upward and back towards the disc. A similar motion is generated for the upper roll pattern. This unique pattern prevents scum and foam from accumulating on the top of the liquid, improves the grit resuspension, and allows for a homogeneously mixed tank. Because the mixing energy is imparted to the sludge through simple harmonic motion, the hydro disc does not collect rags. Rags, if they are present, simply slip up and over the hydro disc. The LM mixer, the optimal solution in mixing and energy consumption.
Okay, sometimes it's better to see the thing in action like that to kind of get a feel for how it works. So, as you can see, that up and down motion, it creates a pressure wave in the center of the tank, and that's kind of what drives that mixing action. Probably the first thing you notice, very simple design. You have the hydro disc at the bottom, you have a shaft, a seal tube to help seal the connection and not allow any gas to escape, and then it's simply a mixer flange and a drive head. This could be mounted on pretty much any cover. If you watch closely, you can see that up and down motion is actually circular motion from the gearbox translated through a Scotch yoke to create that vertical up and down. Very simple. It's been around forever. It always reminds people of like an old locomotive or something like that. As you saw in the little video, the way this mixer works is creating these pressure waves. So what we're looking at here is a CFD analysis showing velocity vectors through a slice of half of a tank. And as you can see, there's a whole lot of energy concentrated in the center. That center cone or center cylinder is where all these pressure waves are being created. And I like to think of it as it's like someone swinging on a swing, and you keep pumping them and pushing them as they go. It just keeps propagating those waves. So these waves, they get pushed down, they'll scour along the bottom of the floor, and we try to design these and pick the size of the disc and the length of the stroke to keep velocity such that it can keep grit suspended along the bottom of the tank. And then you can see as it hits the wall, it curves back around, and you have the same type of flow pattern up on top. That pressure wave flies up, hits the surface, propagates out to the wall of the tank, and then it's subducted back down and curls around back towards the center. So that's kind of how the mixer works. You're creating pressure waves, and the geometry of the tank is what's helping you to do your mixing. What happens if you have a very large diameter tank with a very shallow wall? Well, then the mixer doesn't work as well, because as you can guess, that velocity wave along the bottom, it runs out of steam, so to speak, before it can hit the wall and get turned around. So there are geometry factors to consider in tanks. And if it's a very large tank, you might need multiple mixers in place. So we have numerous installations. I think we have over 150 units installed now in the United States. They're gaining in popularity. And part of the reason it's very popular is it's easy to fit on any type of digester. You can put this on floating cover, fixed cover, truss covers, beam covers, shell covers, concrete covers, you name it. It could be an open tank with a bridge. These mixers have been installed in almost any situation. We've also got some on some silo or egg-shaped digesters, and also some large pancake-type digesters. We've also used it on a number of different applications, from just traditional wastewater sludges. We've got applications where people are treating foods, oils, and greases and doing co-digestion. And one of the more interesting ones is some blending tanks where they've got about 8% solids. How do we prove that this is actually working? Well, you need to have a number of tests to verify that it's working. The most easy one is the computational fluid dynamics. That's all done on the computer. It simulates the hydraulic flow patterns. So we can do that for your applications. If you have a tank geometry that you think this might work, that's a simple way to plop one of these in and see if it looks like it would show good results. On other installations, we've done solids profile testing after the actual mixture has been installed. We've done temperature profile testing. And we've also done a whole bunch of lithium chloride tracer testing, which has for years been the most common way of testing mixing efficiency in a digester. And generally in these, we've been able to show that with the lithium chloride tracer test, we're achieving about a 95% active volume. Black & Veatch did a great study on this mixer at Ina Road. We've also had numerous other plants where lithium chloride tracer tests have been done and verifications of the mixing efficiency. This all sounds great, but what's even better is that we use a lot less horsepower to achieve kind of the same results with this mixer. So in Ina Road, they had 90-foot diameter tanks. They had some old draft tube mixers that I remember putting in when I first started working and thought they were great, but they had about 90 horsepower. We put in a single LM mixer that was 10 horsepower, and so you can imagine the power savings going from 90 to 10 horsepower per digester. It doesn't take more than a few years before you start to really see a return on that investment. South Shore, Wisconsin, another similar type of situation. They had much larger tanks and they had a nozzle mix system. This used 200 horsepower, and then we put 3 mixers on these tanks for a total of about 45 horsepower. So substantial savings in power. And you remember, these things are operating for the most part 24 hours a day, 24/7, and huge savings over time. Here's a quick video of the guys at Ina Road.
Well, the Ina Road facility was built in '75 and started up in '77. We are modifying it and expanding it now to be a biological nutrient removal process, and it'll have a capacity of 50 million gallons a day. We had a reliability problem. We had 20 of those mixers on 4 digesters. We just had a real problem keeping the mixers running on a continuous basis.
At one time, I had on each one of these digesters, I had 5 mixers. I had a crew of 3 full-time working on all the mixers all the time.
So we were looking for something to reduce all of our costs and increase reliability, and that's why we looked into the linear motion mixer.
It's so basic, there's very little that can go wrong with it.
It just works with an up and down motion by moving the liquid and the solids around and keeping them in the solids in suspension.
Now, one guy can come up and do preventive maintenance on them, and we have very, very little trouble with them.
We produce a lot of our own electricity here with the methane gas, but we're utilizing it a lot more efficiently than we were before. And when we put the linear motion mixer in, we were saving approximately $30,000 a year in electricity per digester, and we have 4 digesters at that time. So that was $120,000 in electricity alone that we saved by going with the linear motion mixing system instead of the rotary. Hopefully it'll be a benefit to the community.
Okay, so the big factor there is the energy savings. That's huge for a lot of these plants, especially with multiple digesters. It can really add up fast. So just for example, if you had a 20 horsepower linear motion mixer versus 100 horsepower, over a 20-year lifespan, you're saving close to $1 million. So Ina Road, first mixer was installed in 2003. They decided to clean out the digester in 2008. There was a lot of worry that, well, what are we going to find when we clean out the digester? Is it going to be full of grit? That's a big problem in the Southwest. But what they discovered is that they actually had less grit in their digester than they had with their old mixing system. So that was a huge plus, that the LM mixer was doing a great job of suspending any grit and keeping things mixed well. Stevens Point also quoted that they had an increase in biogas production, which is something that was maybe not expected. We'd like to claim that it does as good a job as any other mixing system, but they reported that they actually saw an increase in gas production after installing their LM mixers. So the key points of the LM mixer: low operating costs, low installation costs, large installation database, very efficient mixing, and with over 150 units out there, proven technology. So if we've got good mixing, we go back to our recipe, we're producing good gas, what are we going to do with that gas? Well, most places, they want to be able to store it to utilize it. It's rare that you can just burn it off as fast as you're making it. You need to keep a volume to kind of drive a boiler or engines or turbines. This isn't a new thing. Back during the World Wars, people realized that biogas could be used as fuel. Gasoline was maybe not as available, so they came up with ways to store biogas to use in cars. These days, we can mount these membranes on existing tanks, on slabs. They're very easy to put in. Very high capacity gas storage. A lot of times footprint might be an issue, but if you have a small space where you could put a concrete slab, you can easily fit a membrane cover for gas storage if you need additional gas storage on some existing digesters. And one of the key advantages of the membrane is the volume that you can store. So if you look at this chart, what we see is the cover diameter here on the bottom. So as cover diameter increases, you can see that for a steel cover, you don't really gain a whole lot of gas storage capacity as the diameter increases, but it goes up dramatically with the membrane cover. So around a 100-foot diameter cover, your steel cover might only store 50,000 cubic feet of gas, whereas your membrane is going to store around 250,000. Now the one downside is for these membranes, the larger the diameter and that larger volume of gas, you have to have a lower operating pressure, because as the pressures increase, the stresses in the membranes get very high. So usually what you'll see is some kind of a booster pump after the membrane if you're doing those very large sizes, just because the operating pressure inside the membrane is lower. So another tricky issue with membranes is how do you know what membrane to specify, or what material to use, or what type of yarns, and what's the weaving of the weft, and there's a lot of craziness involved with it. The approach we like to take is think of a membrane cover the same way you would think of a steel cover. If someone was supplying a steel cover, you would never specify what type of steel needs to be used or what's the recipe for the steel. You'd simply say, perform an analysis on this design based on structural building codes. So we kind of take the same approach with the membranes. When we're asked to supply one, we'll look at what are the design loads. Is there wind to be taken into account, or snow issues? And then we will do an FEA analysis on the membrane to determine what's the material that best suits this specific project. We can sign our calculations, stamp them with a PE stamp, and it makes it a little bit easier for whoever's responsibility it is to approve this design. And it removes the responsibility to become an expert on membrane materials and just simply look and say, well, there was an analysis done, it's been stamped by a PE, these are the criteria involved. It treats it more like a steel cover. So here's just a quick shot of like the FEA analysis. There's special software required to do this because you're dealing with multiple axes, and this material is going to stretch under loads. What you generally see with any membrane, though, is that your higher stress regions are up near the top. So we always like to recommend you really don't want to have any connections or access points up near the top. That's your highest stressed area. Now, a common misconception is that these membrane covers are just a single membrane, that if a bird flies into it or it gets scratched, boom, there goes all your methane and it's disappeared. There's actually multiple chambers. There's an inner membrane that sits inside. That's where the gas is kept. And then there's an outer membrane that's kind of a protective shell, and it's coated with special UV inhibitors to help it withstand more sunlight. And so you have an air chamber in between those two sections. So here in the purple, that's where all your methane gas is going to be. And then that space between, air is constantly being blown in there. And we have a purge valve that's constantly relieving air. The good thing about this is that because you're constantly pushing air through there and relieving it, you have very limited chance for methane to build up inside that space. Now let's say there's something that happens, your inner membrane tears. You can also have a methane detector there to make sure you're not getting methane leaking out of the system. Another thing that you want to know is how much gas do I have in there? I have to have some way of knowing how much is in there. I can't just look in and see really. So what we do is connect a load cell to a spring on the top, and that will tell you how inflated your inner membrane is, and it correlates to how much volume you have available. And here's just a quick picture. This is what it looks like on the inside. This is that airspace between, and then underneath that black is where the actual methane would be stored. So great option for gas storage. How does it compare with a steel cover? Well, steel cover, longer life expectancy, generally around 30 years. Membranes, usually only about 15 years. They're highly susceptible to UV degradation. So if you're up in Wisconsin, they're going to get a little bit less sunlight. They might last a little longer. If you're down in Florida, a little more sun, life might be a little bit shorter. Installation costs, steel cover, very high. Membrane, it's relatively low. And most membranes can be installed in a matter of a week or so. Capital costs pretty average for the steel cover, low for the membrane. Gas storage, that's where the big difference is. The membrane is going to give you maximum gas storage. And then operation pressure. Well, steel cover has the advantage there. You can generally run a much higher operating pressure with a steel cover. It's usually just a question of adding how much ballast you want to overcome that internal pressure. And then both of them, fairly little maintenance. Main thing with the steel covers though is that steel will corrode over time and will probably need to be repainted at some point.